Good morning all. This is M. Paramesh, convener of 5-day online faculty development program on recent advances in electrical engineering. Welcome all for day 5 session. On behalf of Department of Electrical and Electronics Engineering, Gates of Technology, I thank each and everyone for your active participation for day 4 session. I hope you all had an interesting and knowledgeable session on day 4 on role of forecasting in renewable energy generation by Dr. Damodara Sivakrishna Rao sir. And I hope all of us get new research ideas by the end of this 5-day FDP. Now it's time to start our today's session. I request Mr. Lakshmanath sir to introduce today's speaker.
Good morning, sir.
Yeah, good morning
all. Myself, Lakshmanath, Assistant Professor, Department of EEE. I take this opportunity to invite an intellectual person, Dr. Umesh BS, Postdoctoral Fellow, Khalifa University, Abu Dhabi, UAE. Sir completed his BTech in Electrical and Electronics Engineering from University BDT College of Engineering, Devanagari in 2007. MTech in Electrical Engineering from NIT Warangal in 2011. And PhD in Electrical Engineering from IIT Hyderabad in 2016. He has over 5 years of teaching, industrial and research experience. Sir has abundant knowledge on various research areas like performance improvement of multi-phase induction motor drives, multi-level converters for renewable energy applications, design of new power converter topologies for EV battery charging. His publications speak about his experience and interest in research. To his credit, he has 4 international journals and 9 international conferences. Sir received various awards, that is Engineering Innovation Award, Mustang Program, GE Aviation in 2019, NAMPET a Research Award for Best PhD Thesis, CDAC Thiruvananthapuram in 2017, Excellence in Research from IIT Hyderabad in 2015, and also Sir has Best Paper Award from IEEE ICIAFS Conference in 2014. He has published a patent with US Patent Khalifa University titled Direct Electric Vehicle to Vehicle Charging using EV Drivetrain and motor windings. I welcome Dr. Umesh BS sir to take over this session and enlighten us with his experience. Thank you, sir. The session is all yours.
Yeah, thank you very much. Thank you very much for the introduction. So, all viewers, hope all are doing good in this COVID time. Yeah, we will start our discussion today on mainly my present work is on EV charging. In particularly, it is in vehicle-to-vehicle charging. Okay, so this is this presentation I made more generic, like all the EV charging options available right now, and what are the topology of converters used in that all the applications or all the present trend what is in the charging, and later I came to what is V2V vehicle-to-vehicle charging. And then how to go for a wireless charging. That's the flow where I'm following. Basically, we will first go through the fundamentals of charging, like the EV architecture and all those things. So as we go, we will see that the flow is a flow I arranged in a way that even for a basic, without any knowledge in EV charging, should understand the things. So that is how I arrange the slides. So without delay, we will start our thing. So basically, the electric vehicles, if you come to, there are initially there were hybrid architectures, like IC engines well, like initially for many years we are with IC engines. Now with the concern of environment and global warming, so we are moving towards electric vehicles. So there are various combinations came before the full electric vehicles, where you have a non-plug-in hybrid electric vehicle. In a sense, you have IC engine. In parallel, means in addition to that, you have one more motor and a battery storage. Whenever you brake or whenever you do braking while driving, so your regenerative braking will happen, and the energy of your kinetic energy will be stored into the battery, and it will be used whenever you have a less fuel, petrol. At that time, you can use the stored energy in the battery for driving the vehicle little further. So this will add little mileage to the vehicle. Like if a IC engine is giving around 14 kilometer per liter, so with the battery and the means hybrid combination, you will be able to go for further like 17 kilometer, 18 kilometer per liter. So that's a boost. So that is the initial stages of developing the electric vehicles. So and later it came like why only charging by the regenerative braking? You can charge these batteries by externally also, like from the grid. So that is called a parallel plug-in. So you can plug in parallelly, and later they increase the battery capacity and IC engine become in series with it. So like that. Now presently you see many cars which are full electric vehicles like Tesla, Nissan Leaf, and many others are coming up like Sona Motors and all those things. Okay. So basically, if you go a full electric vehicle, the architecture will be as a kind of the figure shown below. That is, you will have charging ports and at the front of the vehicle or the back of the vehicle, at the side of the vehicles. They usually call, there are three types of charging ports like CCS2 combo. CCS2 combo is a combined version of AC and DC charging, where you can see the lower, you can see my cursor, right? Or yeah, it's okay. So CCS2 combo, in that you have the top portion of it is a AC charging. You can feed in the single phase AC or a 3-phase AC input, or and the bottom it is a DC. So the DC terminals will take directly the DC fast charging station. From the DC fast charging station, you will be connecting directly to it. The same CCS2 combo, when you split into two ports, it will be a type 2 charger. Type 2 charger and a DC fast charging charger port. So this is about ports, and after that ports, there will be a onboard type 2 charger, which is a power factor correction unit, where you will convert the AC, which is input to the AC terminals, to DC, and that DC will be again converted to battery voltage. So and the battery will be charged. This is the flow where the onboard charger works. The onboard chargers are of low power. They are mainly, if it is a single phase, it will be 3.3 kilowatt, and if it is a 3-phase, it will be up to 19.4 kilowatt. The charging time will also depend on the power which you are seeing. If it is 3.3, you need to charge overnight, like up 12 to 14 hours. And if it is a 3-phase higher power charging like 19.4 kilowatt, you can charge the whole battery within 6 hours. And the other option is DC fast charging station. You go to a station and wait for 1 hour and take it. You will be charged. You will get full charge within 1 hour. That is a DC fast charging. The only difference with all this thing is the charging current to the battery. If you increase the charging current to the battery will charge faster. But there is a limitation on it. So the thing is the temperature. So if you charge the battery very fast, like with a higher C rating, like around 3C rating, the battery will get heated more. So your cooling system should support whatever your charging rate is. So that is the main concern while charging the battery. So this is mainly the charging thing. Other architectural thing is like main thing for EV is to run it. To run it, we need a motor and a inverter. Okay, from the battery, the DC-DC converter will, it's a bidirectional DC-DC converter. It will convert from the battery. It will go to the inverted DC link, and the DC link will supply the inverter will supply AC, required AC for the EV motor. So the EV motor will drive the vehicle. So this is the whole architecture of electric vehicle generally. But there are cases like the EV motor can be PMSM or induction motor or a switched reluctance motor. So in case of induction motor, some architectures are using this battery side DC-DC converter. if it is a PMSM, there is no need of this DC-DC converter. You can directly connect the battery to the inverter, drivetrain VSI. Okay, so that is whole about the architecture, and the other loads are your car AC, car lighting, and some other loads in the for just startup. There is an auxiliary battery that also you need to charge. So these are all the things which you have in electrical components of the mainly the major components of the electric vehicle. So this, you hope you understand this architecture. So based on this architecture, I'm going to explain how the charging things happens, different charging types and different charging things will happen. Okay. So coming to types of charging commercially available in the market. The first one is onboard charger, which is in a home. So if you have an electric vehicle, you can charge your electric vehicle in the home with a little more bigger current rating socket. You need only a bigger current rating socket, like 19 amp socket. And the charger inside the car for the single phase AC charging is around 3.3 kilowatt, and it takes around 17 hours. And it can it takes for full charge around 17 hours. So if you come to some public AC chargers which are like type 2 chargers we call, or level 2 chargers, they are a little bit higher power. You can see in the second figure where they will be of 19.2 or 19.4 kilowatt or even 11.2 kilowatt. It depends on who is installing it, who is the manufacturer, all those things, and even with the supplier who is supplying it. So it's around maximum of 19.4 kilowatt, and the current will be 80 amps AC current, and you will need only up to 6 to 7 hours to charge the vehicle. So you can go to office and wait until you finish your day. The vehicle will be charged by evening. So it's best suitable for parking lots and in the office infrastructure. So that is one thing. And if you are going for a long trip and in the road, there will be DC fast charging stations. So already maybe in India, you have known that the Tata Power or Tata Motors is establishing a huge DC fast charging stations throughout the highway. So these are from mainly of 50 kilowatt to 450 kilowatt. 50 kilowatt to 150 or 200 kilowatt is called DC fast charging station. About 200 kilowatt, it's called extreme fast chargers, where they will charge the EV battery within 10 minutes. So, and these 50 kilowatt guys will take around 50 minutes or 1 hour to charge. So this is like a experience for the EV user, like a petrol filling. So in 10 minutes, the vehicle will be charged and you are ready to go. So these are the basic charging types which are available commercially right now in US. If you see, all these are available. In India also, we have all the things, but the numbers are only different. Like the number of charging stations are less. Still, the EV users are less in India. So that's why we have lesser charging stations. And as the EVs increases, even charging station and every infrastructure will grow. So now the government of India has made EV charging station. If you want to own an EV charging station, there is no need of license. You can have a business. If you have money, you can have a business of EV charging station of your own on a highway. So that needs some permissions, but don't need any license. The government will decide where to keep the station, but you should have investment. That's all. No need of license like petrol pump. Petrol pump needs a license to have it, right? So this is mainly made to motivate the this is just to accelerate the EV revolution and to make EV replace the IC engines by 2030 or 2050. So that is the main motto. So coming to next thing is, what are the challenges in this? So if you see our EV, is everything good? Our EV don't have any disadvantage? No, it has a lot of not lot. It has mainly this disadvantage like range anxiety. Range anxiety is such that you leave your home and you have a travel destination target, like around 500 kilometer, and you know your vehicle can give up to 600 kilometer. You assumed it, but at the last moment, you because of some efficiency issues or with the system constraint, you may not achieve 600 kilometer, and you will get anxious when the charge is almost near to exhaust. So that is called range anxiety, and you are worried whether I get a charging station again or I need to wait there, or those things are the anxiety for the user who is using the electric vehicles. And this type 1, type 2 AC chargers, as I described previously, they are very slow, and you need to wait. Like even if it is a type 2 charger with 19.2 kilowatt, you need to wait. It's very slow, like 6 hours it takes, and you need to be very organized, and you need to plan well to avoid this range anxiety. And coming to DC fast charging stations, you can't have by individual user. That needs a company to set up these DC fast charging stations. And these DC fast charging stations are very less in number presently in India, just because the EV users are less, and it takes time for companies to set up EV charging stations. Now it's the tender has gone, and many big companies are quoting to make charging stations throughout the highway. Okay. So these are the challenges, main challenges in EV charging. And if you come to basically charging, coming to the topic where research topics, where what is the topology used in EV charging, type 1, type 2, and DC fast charging stations. How is the structure of topology, if you want to know? So you have basically a diode bridge rectifier, which is basically converting a single phase AC to DC, and then followed by a power factor correction circuit, which is a boost converter, you can see, and that followed by a DC-DC converter stage to make high frequency AC, and then it will go to for another DC conversion, and finally it reaches the battery with some filter elements. So this is mainly to ensure this AC, the EV charging should not affect the grid. The power quality at the grid should be good. There should not be variation in the frequency and the voltage just because of EV charging. So that is the main concern. So for that, we are doing power factor correction. For any EV charger, power factor correction is must. And if you go to how the power factor is controlled, so yeah, these are another different topology where you will see a full bridge diode rectifier. After that, there is an interleaved push PFC just to increase the power rating. And after that, again, a resonant converter. Resonant converter mainly ZVS and ZCS, zero voltage switching and zero current switching, which will reduce your switching losses, and it will improve the efficiency. That's the main concern. So there are a lot of hundreds of topology for this 3.3 kilowatt already published in the literature, and there are still to come. So many people are publishing on this area, and you have a lot of options here. Okay. And the other thing is with a single stage charging, where you don't have a diode bridge rectifier, you are doing AC and DC conversion together. So that is another type. That depends on your application and the power level. So the next is how they are controlling this PFC rectifier. So basically, you will be sensing the voltage and the current, and you will actually maintain the DC link voltage. If you see the DC link voltage is measured and it is compared with the reference, and the error will be fed as a current reference, and that current reference is multiplied by a unit voltage vector, that is same as it will be a sinusoidal vector, and after that again a PI controller which will make you PWM pulses for the PFC rectifier. That is how the control works. So it's mainly a single phase power factor correction, which is very well established already. So this is how the power factor correction works, and after that there is a DC-DC converter and charging the battery. So this is the single phase type 1 3.3 kilowatt battery charging topologies and their control. If you move on, it is type 2 charging, where you will be having a front end rectifier, you can call it as. It's a rectifier, controlled rectifier with input filters, You have a three-phase supply. After that, you have line inductors. After that, you will be rectifying it and making it a DC voltage. You can directly connect the battery to DC link, or if you want a further voltage reduction, you can have a bidirectional DC-DC converter here after the VDC, after the DC link. So that is a higher power, like up to 19.4 kilowatt you can go, because it's three-phase. Three phase is mainly preferred for higher power. So that is the basic type 2 charging. So the control is similar, but you have here, you can go for many type of control. So basically I represented here is a DQ control, where you need to sense voltage and the currents of the grid and convert them into DQ frame. Means the Clark's transformation and Planck's transformation, and your PLL will give you the theta for the computation of VQ, VD, IQ, ID. And after that, you will be you will have, means whatever you want to control. Like if you want to control on the DC link voltage, you can take DC link voltage error and feed it as a IQ reference, or the real component of the, means the real power component of the current IQ, and that error will be fed, and we will get VQ star, means we will generate VQ star and VD star. Those are the reference voltages for PWM generation. So directly you can't give it to the rectifier because they are in DQ frame. Again, you convert from DQ to ABC and generate PWM generation. Okay. So that will generate PWM for the rectifier to maintain unity power factor at the grid and the power quality at the grid. After that, with DC link, there is a battery side DC-DC converter, and it will be charging the battery as previous. In type 1 also this is common, but this is of a battery side, so it will be of high power. So this is for AC charging. So if you go for a DC fast charging, there are many architectures for DC fast charging. So DC fast charging is not on board. Whatever we talked till now is inside the car. The charger which we talked, the type 1 or type 2 chargers, they are inside the car. And just because they're inside the car, you can't have a bigger power. Like you can't go above 20 kilowatt. Above 20 kilowatt, the converter size and everything matters. So you can't accommodate inside the car, and it will just increase the weight of the car and the space of the car. It will consume. So the user will lose space and weight. Will have more weight for the car. So to avoid that, to increase the power level more and make the battery charging faster, so they have come to a plan where they establish the whole charging circuit, what is there in PFC rectifier stage, and from the AC rectification to DC-DC converter, everything outside the car, and it is called DC fast charging station. So from the DC fast charging station, it is again the same structure, where from three-phase AC is a high power like 50 kilowatt, 100 kilowatt, up to 450 kilowatt. So from that high power, they will be rectifying that high power to DC using active rectifiers as explained. So they usually use Venn rectifier or a three-phase rectifier, so kind of things. So you can even go for multi-level options, multi-level rectifier stages. After that, there is a DC-DC converter stage, high frequency transformer, all are there. So after high frequency transformer, this is mainly for creating resonance. Because of the high power and high switching frequency, you need to go for resonant converters. So this isolated DC-DC stage is a resonant converter stage, where you will have ZVS, ZCS to reduce the losses, and the output filter, and then it will go to battery. So this is how the basic structure of a conventional DC fast charging station. So in that DC fast charging station, there are types, like you can have different architectures, like to include. Mainly from the grid, you will have a low voltage, low frequency transformer. After the transformer, you have individually for each module, you have an inverter and a DC-DC converter. An inverter and a DC-DC converter, they are bidirectional. You can pump back to the grid, or you can take power from the grid. Both the inverter and the DC-DC converter are bidirectional, And the additional advantage is with the bidirectionality is you can pump power to the grid from the solar or the auxiliary batteries like energy storage. Now in power system, it is more batteries are coming just to make a grid farming inverter and to have a inertia simulation, all those things. So this is mainly this structure is convenient for renewable energy integration, where you can directly feed the renewable energy sources and the extra batteries which you have, and it's bidirectional. You can take from the grid and you can give it to the grid. So that's the main thing. And after that, the next architecture will be you have a centralized inverter. Instead of having inverter for each module, it is a centralized inverter which converts the overall. It has a big high power, means the instead of distributed inverter, if you have a distributed inverter, the power will be distributed throughout different modules. Each module will have some power. The total power will be distributed. Here, it's a centralized inverter which will be rated for all these DC-DC converters. Whatever power they are consuming, the sum of the powers of these individual DC-DC converters should be managed, or the inverter should be rated to handle that power. So after that, there are, as usual, the DC-DC converters are there. Even here, it's bidirectional. You can pump to the DC link. It's like you are forming a DC bus after the grid. So instead of AC grid, you are forming a DC grid here, and the inverter is centralized. That's the difference. So the next thing is you have a inverter with a high frequency transformer. This is called solid state transformer, and it is very efficient compared to a low frequency transformer. So after the inverter output is given to a solid state transformer, where it can convert DC to DC, and again a bigger DC to DC will reduce it to a required DC bus voltage, and again the same as previous architecture. Okay, so these are the different DC fast charging station architectures. Till now what we are talking is everything commercially available. So but it has implications on the grid, like you will have as the penetration of EV goes behind 20%, the problems with the grid will be pronounced. Like you will have a lot of load shedding, all those things, like grid will be disturbed. And if you go more and more without a backup, without a control structure for the grid quality maintenance, you will be losing the grid stability. So they have some standards like THD of the charger should be kept within 25 to 30%, and the permissible limit on the EV penetration should not be more than 35%. If it exceeds, you need to have a bigger transformer and bigger grid facility. So this is like these are the main implications on the grid. So to avoid this, you can have a different alternative charging options. And this is one problem we are facing. There are other problems like, so now we are coming to my main research area, that is electric vehicle to vehicle charging. Okay, so before that we have one more recently published from Professor Ned Mohan's lab. This is Narimani. So this is from a paper from the Professor Ned Mohan's lab, where they have a centralized three-level inverter, which creates a bipolar DC. The advantage with the bipolar DC is you will have more number of charging modules, like you can charge more vehicles in a single station. So that is the main advantage what they are claiming here. You have a 3-level inverter and a 3-level DC-DC converter, which will be, so if you see the centralized NPC converter is a 3-level inverter, and the DC-DC converters near to each car is a DC-DC converter, 3-level DC-DC converter. So that will take power from the bipolar DC and convert it into a DC, which is matching with the EV car battery voltage. So this is like again a fast charging station with multiple options to charge more EVs, and even it has possibility of integrating PV and the battery. So this is a very new paper, if you can see. So this is in 2020, like that, very recent development. And here they are claiming, or they are addressing the problem of this voltage, capacitor voltage balance at the output of the inverter. So usually these capacitor voltages will get unbalanced because of the switching, multi-level switching. To avoid that, they are proposing a control technique. You can refer this paper. So I'll be sharing the reference later. Okay. So this is one of the recent publications. So this gives a direction where the DC fast charging stations are going. You can have, this is like modular, and you can have more number of EVs get charged using this. Okay. And this is another paper from Professor Beam Singh lab. So this is like power factor correction, or the power quality improvement using for a EV charging. So where they are using solar integration and another EV also integrated to the DC bus, and another battery integrated to the EV. They're forming, basically they are forming a this one DC bus. It's a multi-port converter, you can call it as. There the power is coming from electric vehicle and battery and the solar, and it is forming a DC bus, and the DC bus is converting the DC to normal AC, grid AC, and even the grid is integrated. The vehicles for AC charging, the vehicles can use from grid or from the solar based on the availability. If solar is available and battery is available, solar is more available, you can charge the battery, charge the EV. So like that, there are many combinations possible in this architecture. This is one more multi-port converter, you can say. So that will give you more flexibility to integrate the renewable energy sources, batteries, and the other EVs also. This is a type of electric vehicle to vehicle charging. You can give power from your vehicle. So that means when the peak demand is less at the night times, everybody is sleeping and they're not using power. So you can charge your vehicle at a lower tariff from the grid, and at the daytime everybody wants charge. So at that time you can sell the charge. So that is the one advantage with this. That's advantage, general advantage with the electric vehicle to vehicle charging. So we will go particularly to this electric vehicle to vehicle charging. This is just one option which is explored in this paper. So the next thing is this is like home PV solar rooftop integrated for EV charging. So there is a solar and there is grid, and there is a solar and the EV. So from the solar, the PV converter will convert and make it DC link. It's same as previous paper, but in a different way. Like it's for a different applications where you have a solar rooftop and you want to use that solar rooftop for EV charging. So at that time, this combination of the converter will work. Like there is a grid converter, there is a PV converter, and there is a EV battery converter. So you can give it back to the grid. You can take from the PV, or you can give the PV power to grid and later you can take back. So all possible combinations. It's a bidirectional chargers again. So it's mainly an EV. Thanks to the bidirectional converters, you can actually control the power flow in whatever direction you want. So coming to the challenges in DC fast charging stations, it's a huge initial investment and regular maintenance efforts. You need to manage it. It's like an industry, and it's a big charging station. You need to manage. Like it's not like a petrol pump. There are also maintenance required, but this needs more maintenance. And grid stability and power quality are the important issues, and complex control integration of renewable energy sources. So when you integrate renewable energy sources, definitely you need a control to maintain the grid stability and to control the power flow from the energy sources, and when like that. And this is an extra investment for the EV manufacturers to establish DC fast charging stations. So these are the challenges. I don't say they are critical challenges. When you want to charge the EV very fast, DC fast charging station is very good. and it is like charging the vehicle within 10 minutes to 1 hour. That is a more advantage because already all the users are used for the fuel petrol station where they go and within 10 minutes they are, not even 10 minutes, 5 minutes, they are filling their petrol and going. So they want that experience. They don't want to wait for one hour, 2 hours. So in that case, yes, DC fast charging station is a very good option. But when you are going for when you don't have any option, let's say you don't have a charging station, let's say you are not in home, you are stuck in a road in the middle of a highway, there is nothing, you cannot go for a charging station, and your EV's charge is fully drained and you are stuck in the highway. At that time, we thought that there should be some options. It even happens in the IC engine vehicles. It happens like, so the gas, mainly in Europe and US, they are gas filled vehicles. So there the gas is completely over, then someone will bring a cylinder and fill the gas and the vehicle starts. So in the same way, for electric vehicles, when they are stuck in emergency, there should be a rescue system. That rescue system is these alternate fast charging approaches, which we proposed and which we are doing research on. So the mainly this alternating charging approach is, okay, before going to alternative charging approaches. So this is the alternative charging approach where there is no charging station, but you have some DC source or a single phase AC available. I still not moving to electric vehicle to vehicle charging. I'm still discussing one more type of alternative charging where you are saving. See this, as I told, DC fast charging station require an higher infrastructure, right? So we want to avoid that high power infrastructure like 50 kilowatt, 100 kilowatt or 450 kilowatt charging stations cost a huge investment in crores you need to invest. But what we observed, or what the people in research observed, is that already in the electric vehicles, the drivetrain and the inverter for the drivetrain are high power. Usually if you take Tesla is having a 250 kilowatt motor and equivalent power rating of the inverter, and which will be driving in the drive mode. But when these vehicles are at stand, means they are not in the drive mode, and when you are parking it, this high power drivetrain system is unused, like it is not used at all. But instead of that, we are setting up an external high power rated converter system. So the people thought, the researchers thought, why can't we use this and reduce that high investment for DC fast charging stations? So there comes the integrated drivetrain integrated charging options. These are also fast charging because they are high power. So basically what is happening here is you are charging the vehicle using the drivetrain. Already drivetrain, what I mean by drivetrain is the battery, the DC-DC converter and the inverter, high power inverter, which is supplying the motor from the battery. But if you look at in a reverse way, this inverter can be used for converting the AC input, and that DC can be given to the battery by through the EV motor windings, or you can avoid EV motor windings. If you see here, your these 3 star connected windings are a EV motor, and this is a thyristor based inverter, which is here what they did is for a normal mode of operation, they will connect the motor and they will drive the motor from the battery through the inverter. If you when the vehicle is at standstill and you are not driving, at that time they want to use this inverter, not the motor windings here. Further we'll see there are topologies which are using motor windings also. But the single phase AC is connected to 2 legs of the thyristor inverter, and later it is converted to DC-DC and the battery is charged using that. So the basic funda here is basic observation here, means basic principle here is to use the high power drivetrain system for charging when the vehicle is not in drive mode. Like when you are not driving, when you are standstill in the charging stations, you can use that drivetrain for charging. That is the basic idea. This is first published in 1985, where that time there no EV, no much progress in the commercial EVs. So further, when the things going good for EV, further they came up with a stage where they have an external rectifier as a LC filter, and the output of that is a DC. From a AC, they are rectifying it to a DC, and that DC is connected across the neutral and the negative rail of the battery. So neutral of the motor, this L is a windings, 3 windings of the EV motor. So from here they are connecting a DC, and using this inverter or the voltage source inverter as a interleaved DC-DC converter. Okay. Now these 3 windings will become interleaved DC inductors, and machine windings will become interleaved DC-DC inverters, and the inverter is used as a DC-DC converter. It's a interleaved because there are 3 legs. In each leg the current will be shared, the DC current, and then after the conversion into DC, the battery will be charged. So basic point here is that they're using even the motor windings for charging during when the motor is at standstill, they're using. So here is a DC voltage, so the motor will not rotate. Basically you are applying DC currents into the EV motor. The motor is a AC motor, it's an induction or a PMSM, but you are pumping AC currents. Okay, DC current. So the motor will not rotate for DC currents. It will only generate some harmonics, and if you maintain a lesser current than the AC currents, the motor will not even heat up. So there is no harm to the motor but for using it in a charging station. So that is the one important progress in this integrated drivetrain integrated charging. So similarly, there are many topologies. So you have here around like single phase AC. For this is for a 2-wheeler applications, where it is same as previous topology, where you have a rectifier, and rectifier will be feeding to the neutral of the motor and the inverter, and there is a DC-DC converter, and it's charging the battery. Similar way. So the rectified voltage. So this is the whatever extra hardware components is kept here. Okay. This is mainly called, this is a segment of EV charging. It is called drivetrain integrated EV charging. Okay. So coming to the next thing is they wanted this, they wanted to eliminate that extra rectifier outside the car. They want to directly feed the 3-phase AC to the EV motor windings. So, but the problem with feeding 3-phase AC to EV motor windings is the motor starts rotating, because motor is a AC motor. When you provide 3-phase AC currents to the windings of the motor, motor will start rotating. So when you are charging, the motor should not run. if you are during charging, if the motor starts running, the vehicle starts running. So that should not happen. Okay, in charging, the vehicle should be in standstill. So the option is you stop the motor from running by any means. Like you can use a mechanical clutch, or you can do some reconfiguration of the winding, or you feed the AC such that the motor will not rotate. So this is one of the configuration where the AC, 3-phase AC is fed to the midpoints of the windings, AC windings of the motor, EV motor. You can see the electrical machine with split windings. Between the split windings, to the midpoints of the winding, they are feeding the AC. What happens if you feed the AC into the midpoints is the currents gets divided in a opposite direction. Whatever flux produced by the one part of the winding will be cancelled by another part, and the motor will not rotate. That is a fundamental idea here. And rest is after that you will get AC currents here, and that AC will be converted to DC, and after the DC link there is a DC-DC converter which will charge the battery. So basic concept here is to avoid the rotating magnetic field in the induction motor. When 3-phase AC is fed, they are feeding the 3-phase AC to the midpoints. This is one of the configuration to avoid the charging torque. We call it as a charging torque. So charging torque in the sense torque produced during charging. So that should be avoided at any cost. Many people even feeding directly to the windings without the even without the midpoints. They're not don't have access to the midpoints. The main problem here is you need access to the midpoint that nobody will provide for a general normal EV motor. So it's a customized motor in that case, right? So for that, what they did is they started feeding directly the EV motor, but still the EV motor will start running. To avoid that running, they're using a mechanical clutch, which will stop the motor from running. Okay, so that is the main, that is one more topology, which is very basic, and many people have proposed it to three, 4 papers. They are using mechanical clutch also. So that is lossy, like you are stopping something mechanically, something, so that will create a lot of losses. It's like blocked rotor test. So that should not happen. So that's why this midpoint feeding came. And after the midpoint feeding, they went with the multi-phase machines, where this is also similar concept, where they are feeding into the midpoints, but it's a multi-phase. You will have more advantages, like the power density is higher. All the advantages of multi-phase machines will come up. Okay, so this is similar, like you can see the AC, 3-phase AC is fed to the midpoints of a 6-phase machine. So 6-phase machine, each winding is divided into halves, and to the midpoint it is feeding. Okay, so that is how it is. And after that, there is a dual inverters, 12-leg inverters, which is parallelly connected, and it will be charging the battery. Okay, so there are 2 midpoints here. If you observe in this topology, for a phase A1 winding and phase B1 winding are forming one more midpoint for the phase A, and like that. So this will almost cancel all the torque produced in the motor, and it will not rotate the motor. That's the main idea here. And then this is one of the base paper for my research, where they are using AC power to the neutrals, like a 9-phase induction motor drive. Where in 9-phase induction motor drive, if you see my PhD papers, there we have explained how there will be 3-phase groups in it. Like if you take a 9-phase machine, it starts from 0, 40, 80, 120, like that. It is a 40-degree phase difference, 9 windings. So in that, if you carefully observe, there are 3-phase winding groups. Like first winding group is 0, 120, 240. The second is 40, 200, and 40, 160, and 280. So like that, there are 3-phase groups, and each have a neutral. So they have separated the neutrals, and to each neutral, they are giving one line. Like A phase is given to neutral of the first 3-phase group. There, what happens is, in all the 3-phase windings of a first 3-phase group, the current is same. That means the motor will not rotate due to this excitation. The current is same in all the 3 phases. And similarly, for the second 3-phase group, the current is same, which is a B phase. And similarly, for the third, it is C phase current, but which is equally shared between the 3 windings of the last 3-phase group. So that avoids your rotation of a 9-phase induction motor during the charging. So that will charge it's a 9-phase inverter after that, and that will charge the EV battery. Okay, so this is one of the base paper for me. And coming to electric vehicle to vehicle charging, basically this is a new area of research. It is electric vehicle to vehicle charging, which is very convenient and flexible, because anybody can charge any car. Like if you have a EV, you can charge any other EV. Like it is a cooperative energy sharing. It's possible to share energy between the EV users cooperatively. For that, we need an interface. Like you can't connect 2 EVs directly. Like you have on the, as I explained previously, on the EV, there are many ports. Like the one is the DC fast charging port, other is a AC port. You can't connect any of them to charge EV to EV, because they are like, they have some protocols, they don't share energy. And if you connect both the battery terminals directly, the DC fast charging stations, there will be like a huge inrush current and it will spoil the batteries of the EV. That's the main thing. So to avoid it, we need to have an interface. The interface is, there will be a power interface or a software, there is a need of two interfaces, like power interface and software interface. Power interface is mainly to actual hardware required for the power transfer between the two EVs. Means one battery and the other batteries are connected. Now we want to control the charge flow, like who is the provider, who is the receiver, and how much charge should be sent from the EV1 to EV2. All those things the hardware has to decide, and it has to control that power flow direction, all those things. Coming to the software interface is required for the EV users to communicate and decide. Okay, so let's say one EV user is stuck in a road, in the middle of the road, and he has very low charge, he can't move further. And at that time, with the software interface, he can broadcast. To reach a nearest charging station, I need 50 kilometers of range. Okay, for that equivalent amount of energy, if someone can provide me, I'm in this location, you can come and provide me. So that is the announcement he do on the software interface. Software interface is like a mobile app. It can be a mobile app or it can be your car computer. Okay, so using that, he broadcast. So with that request, we'll go to every user, like it's a Uber, when you book a Uber car or a Ola car, so it will go to many drivers, right? So similarly here, it will go to many users, many EV users who are having more charge. Like someone who is near can come and provide the charge required for him, and the excess charge, it's not that all the charge of the other provider will go to receiver. The provider will say back, like he will reply back, I have this much excess power and I'm ready to give with this much distance and this much price. So he will tell those price details, his availability, and how fast he can come to that place, location, and like that things. So these communications will happen with the software interface. And this software interface and communication aspects, there are many papers on V2B. So already a well explored area where you can see on the right side, there is a figure where they are matching the vehicles for V2B transfer. All this software or the communication aspects papers, they assume that there is a power interface already available. Means they assume that there is a bidirectional charger available to exchange energy between two EVs. That is their assumption already. But actually, if you see in the literature, there is no particularly a charger defined or designed for electric vehicle to vehicle. Very few papers, the two or three papers, they are having vehicle to vehicle energy transfer. So in this area, we were doing the research. And this is again the same where they are matching. So here in the left side figure, they are assuming that there is very futuristic. Here they are assuming that the power is wirelessly transferred, like from a tower, the mobile tower. Now we are receiving a signal. In the same way, they are assuming already that the power can be transferred through radio waves, and the vehicles on the road can be can receive energy from those transmitters. That is a very futuristic approach. Maybe in future, after 100, 200 years, it may come. I don't think it's in the near future. That is one kind of proposal in some of the papers. The other thing is a centralized aggregator, where you are seeing many cars are connected to an aggregator where their data will be stored. And this aggregator will decide who can share charge to whom, or who is in an exact position, who is the receiver, who is the provider. All those decisions made by the central aggregator. So these papers are already there, if you see. So, but coming to the power electronics part of it, if you see the required hardware for this vehicle to vehicle charging, this is one of the paper where they call it's an dual active bridge V2b charger, where they have two dual active bridges connected through a transformer, where they are transferring power from one vehicle to another vehicle, or one vehicle to the grid, or one vehicle to the home, or in other direction or bidirectional way. So however you want to control, you can control using this structure. But the main problem is this, one of the controller is they are considering it as an onboard charger already on the vehicle. So that has a power limitation, and it will be like the limited power, you can't have a faster charging, and this is limited with a lower charging rate. You can't charge the vehicles faster, V2B. And this is not a particularly a paper which discusses mainly or majorly focuses on the V2B. This focus on many aspects, and V2B is a part of this paper, where it makes G2B. G2B is a grid to vehicle, and vehicle to house, vehicle to grid, and vehicle to vehicle. So these are the four aspects discussed, and vehicle to vehicle is not discussed in much detail. And also the power rating of the converters are limited, and the charging rate will be limited, and you will have a slow charging. Even if you do vehicle to vehicle, it will take time for both the users to wait for vehicle to vehicle transfer to happen. Okay. The next thing is the EV charging. So this is another paper where they are using an off-board charger. So what you can see here is there is a Tesla and a Nissan Leaf getting charged through a V2B charger. This V2B charger is not inside the car. It is an off-board charger. Basically, in the previous paper, as you saw, there is like half of the charger is inside the car, already existing onboard charger, plus some off-board interface they were using for charging the vehicle from one vehicle to another. But here in this paper, this is another paper. Oh, sir. In this paper, you have an off-board V2B charger, which will transfer energy between two vehicles, and everything is controlled off-board. Okay, and this is mainly the topology is a dual bidirectional DC-DC converters. That means to say you can transfer power from V1, that is the vehicle 1 battery, to the vehicle 2 battery, or from the vehicle 2 battery to vehicle 1 battery, that is reverse or forward direction, depending on the receiver and the provider, who is receiver, who is provider, and the voltage levels. Voltage level will decide you want to do buck operation or boost operation. So all those things needs to be decided. That is, this topology is suitable for vehicle to vehicle transfer using interleaved bidirectional converter. This is a dual bidirectional, you can call, but this paper mentions it's a bidirectional only. Okay, and the main advantage or the main disadvantage of this topology is the charger is outside the car. Means you need to have extra space, and the user has to pay for this charger. So there are many commercially available chargers like this. Hyundai Kona has announced, maybe you have read in the news, Hyundai Kona has a charger, V2B charging facility, like from one Kona vehicle to another Kona vehicle you can charge. But it is an external charger which consumes your dicky space, like the car storage space needs to be shared for this V2B charger, which is a 50 kilowatt charger, which almost consumes your car storage space. That is not good for EV user in two ways. One is he can't he need to pay extra for this charger. The other is he's losing the space, charging his storage space. Okay, so in that way, this way of off-board charger won't work for V2B. And basically the Kona or even Andromeda, there is another company which also has given an option like this for charging vehicle to vehicle with off-board charger. So with both of them, the problem is it is a company managed, like it's not the users who are interfacing and getting the charging. Like there is an intermediate company like Andromeda or the Hyundai. They have dedicated vehicles which are for this V2V. Like when a vehicle is in a rescue mode, like it is an emergency mode, this company will send a car and that car will charge the other vehicle. So that is the V2V available in the commercially available V2V. But we wanted to develop something without an extra charge to the V2V user. There should not be off board, and we should be able to do it using the onboard things. So that we will discuss now. Okay. And coming to the next paper where V2V is discussed, is he has given all the possible V2V combinations where you can see. This is the first combination is like if you want to transfer power from EV1 to EV2, you transfer from the battery and convert it into DC-DC and convert it into AC and give it to grid. And then from the other vehicle, we'll take it from the grid. So that is like redundant energy conversion. This is one of the possibility. And one of the paper has published it in a very long back. So there's a reason, because what they assume is they don't want to change the configuration. So that's why the one vehicle will always get AC input. So that is the one. This is called AC V2V. So this is a AC V2V with the grid integration. The lower figure is the figure which is below is it's an onboard AC V2V without the grid. So you are converting DC to AC, DC to DC, DC to AC, and then again AC to DC and DC to DC. So this is like multiple conversions. You don't need this much of conversions. With that, they decided like to improve the efficiency, either we should have an off-board V2V, DC V2V, where you are directly connecting the two batteries through the off-board V2B charger. Okay. Other option is use the onboard DC-DC converter. So in the architecture we have seen there is a battery side DC-DC converter, right? So use them and connect them. So that is what they did in this paper. They are connected both the DC links. Both the DC links are connected, but for the power flow. But the major problem with this is we don't have access to these DC links. Means if you take, this is the onboard charger as explained, it's a single phase onboard charger on the left side. It is having a power grid. After that, it is having a H bridge, and that H bridge is connected to the DC-DC converter and the battery. Okay. So what they are doing is CVDC. This is the point where they are connecting the DC links of the two EVs onboard charger. They are trying to connect. Basically, you don't have an access to this DC link that is inside the car, and there is no port available for these DC links. You need to have an extra port for this. So this is not practically possible. So without having access to the DC link, so there is a extra customization for the EV is required to have this type of V2V energy transfer. That is one thing. And as I told, the other paper, which is transferring energy from EV A to EV B, which is converting multiple stages like DC to DC, and HB1 is a DC to AC, and that AC is going to the another car's single phase port, that is type 1 port, and that is again same process from AC to DC and DC to DC and the EVB1. So this is like two stages are redundant here, HB1 and the other DC to AC converter. They are redundant because you can directly connect to improve the efficiency and the charging speed. But as I explained previously, we don't have access to that. So what the other paper which is talking is, as I previously discussed, they are using motor windings. The motor winding neutral is fed from a DC source, and the negative of it is connected to the external DC source. Here you need to understand this is again a drivetrain integrated EV motor based EV charging. So this is vehicle to vehicle. This VDC can be another EV's battery. That is what the concept in this paper. Okay. So this VDC, whatever they are written, so that can be a solar rooftop output, or it can be a battery, or it can be any DC source can be connected here with whatever voltage higher than the V battery or lower than the V battery, and it will be given to the neutral of the EV motor. And now the inverter and the EV motor windings acts as a interleaved DC-DC converter. This is one of the basic concept which even we used for our paper for vehicle to vehicle. Here the problem with this paper is they are considering an additional port. So this is an external hardware for the EV user. So as a charger, you need to carry this external hardware to accommodate higher and lower voltage sources. Okay. So similarly, this is another configurations which is similar to the previous one, where they are feeding the DC voltage to the lower negative rail and the positive rail. Okay, and here you are connecting the DC rails, and when there are modes here, you can see there is a D mode and C mode. When it is connected to the C mode, it is charging mode. Okay, charging mode in the sense you are charging from the external DC source. At that time, you are applying voltage between plus and minus, like negative rail of the top inverter. This is a dual inverter case, and positive rail of the negative inverter. Okay, now you are connecting the other vehicle at VDC, and you are charging the two split batteries from this. So this is also like a DC source, and DC currents are flowing in the EV motor, and there is no charging torque produced in it. This is a dual inverter configuration, and the left side one is a single inverter configuration. And if you connect this to D mode, that is called drive mode, you can at that time there is no VDC. You will be running the motor in a dual inverter fashion with multi-level voltages. So that's the advantage for the EV motor. So this is basically a dual inverter drivetrain which you are reconfiguring for integrated EV charging. Okay, this is one of the paper where they are doing this. So this basically can be included for V2B because the VDC can be another vehicle. So another vehicle's battery, or it can be a solar rooftop like that. Okay. So if you come to with all those papers, you can see that there is a problem of either additional hardware required, or some power rating of the onboard chargers are less, like that. So in our research, this is the proposed and published paper which in industrial electronics. What we proposed is, why not we connect the two neutrals of the EV motor and the negative rails directly. So if we connect them directly, you will have inherently you will have a dual bidirectional charger, which I explained previously. They are doing it as an upward charger, as an extra charging unit. But here we can achieve. So basically we observed, the main funda here is we observed that we can achieve the dual bidirectionality using the onboard drivetrain, inverter and the motor windings. If you see LA1, LB1, LC1 and LA2, LB2, LC2 are the drivetrain inverters. So the EV motor windings, and these EV motor windings forming a neutral N1 and N2, and these N1 and N2 are connected together for V2V charging, and the negative rails are connected for the return path. Now this converter is like a dual bidirectional interleaved DC-DC converter, where you are charging from one vehicle to another vehicle battery through the EV motor windings and the inverter drivetrain. So basically you can control the power in forward direction and in reverse direction, whichever way you want, and you can have a different voltage levels of the battery. VB1 can be higher. The voltage of the electric vehicle 1 battery can be higher than the electric vehicle's 2 battery. Okay. So, or vice versa, you can have any side higher voltage, any side lower voltage, or you can transfer power from this side forward or reverse direction. That is the main advantage of this topology. And it is fully integrated. Like there is no extra investment here. There is no extra space required. Everything is already in the car, and you are utilizing the onboard power electronics for electric vehicle to vehicle charging. That is what makes it more suitable for the cooperative energy sharing between the EV users. Like, see, EV user want to share energy, but he don't want to buy an extra charger. He don't want to spend money for charging another vehicle. So in that case, already the electric vehicle drivetrain is reutilized to make EV charging. Okay, so in that case, there is no extra space required. There is no extra money required for this. So that is the main advantage. And these are the possible modes of operation where you can see the voltage depending on the battery voltage. VB1 is the battery voltage of electric vehicle 1, and VB2 is the battery voltage of electric vehicle 2. And depending on the voltage levels, there are 6 possible modes. If VB1 is greater than VB2, and EV1 is a provider and EV2 as a receiver. In that case, it's a forward buck operation. Means you need to reduce the voltage of EV1 because it is higher than VB2, and power transfer direction is forward. Similarly, other modes like forward boost means you need, if the voltage of the battery EV battery 1 is less than VB2, then you need to boost the voltage for VB2. So that is forward direction boost. Similarly, the reverse. The main advantage we saw here is the DC fast charging. Means you can charge faster than your type 1, type 2 chargers, and even equal to the DC fast charging station. Okay. The EV motor and the battery capacity comparisons are here. So if you compare the different EV available on the market like Tesla, Nissan, Kona, Chevy Bolt, and Renault and Kia Soul, you can see the motor ratings are in the range of 350 kilowatts, 160 kilowatt, 150 or 150. In that range, like they are at a rating of equal to your DC fast charging station. If the motor is of this kilowatt, definitely the inverter associated with it will be of this range. So you have a huge power electronic sitting inside the car already, and you are not utilizing it for a charging. So that is the main motivation comes for this drivetrain integrated vehicle to vehicle charging using the onboard drivetrain motor windings and the inverters. So if you see here, the per phase current rating of the EV motor is around 500 to 125 amps. So that is a huge number which can be used to charge the batteries at 6.5 C rating, 6 rating, or can have at least on an average you can charge it at 3C rating. 3C rating in the sense is a fastest charging, extreme fast charging you can do. 3C or 4C rating. You can charge the vehicles fully within half an hour or even within 1 hour or 10 minutes. That depends how much you are charging, whether you are charging at 3C or 6C, depending on that. But this is very sufficient for the electric vehicle to vehicle energy transfer, because the vehicle to vehicle energy transfer requires only a small amount of energy to be transferred, such that it makes the exhaust vehicle, like the drained vehicle, to a charging station. The amount of charge required is just to make the receiver EV to reach a charging station to make it more charged. Means it's a rescue system, so cooperatively utilized for between the EV users. Okay. So that's the main advantages you can see with the drivetrain integrated chargers. So coming to the modes of operation, you can see here I have shown the mode of operation for one leg of the forward buck mode. If you see, EV1 battery VB1 is a provider. So the power flow is in the forward direction. As VB1 is greater than VB2, the battery voltage will be the VB1 battery should be stepped down to match with the VB2 battery. That's why it is called forward buck mode. So in this direction, what we are doing is we're turning on S1 first, like a buck converter, and the windings will conduct as a interleaved DC-DC converter. So only one leg we are showing. Just because D5 dash, D3 dash, and D1 dash gets forward biased by themselves, we need not to switch VSI2. That reduces our switching losses considerably. And if you go to the then after that, the path for the current will go through the SA2. We will keep SA2 permanently turned on, and it will reach the battery 2 with a stepped down voltage. So that is the operation in forward buck mode for a single leg in the on period of the S1. If you turn off the S1, and D2 will, if you in the lower figure, the D2 will start giving a path for freewheeling. So the freewheeling happens through D2 and the windings LA1, LA2, LB2, LC2, and it will go to all the diodes, and it will just then converge into IB2 and charge the battery. These are the two charging or the charging modes in forward direction, or the operating modes of the proposed interleaved DC-DC dual bidirectional converter. So in this, you can see the energy is transferred from VB1 to VB2 in forward direction with without any extra hardware required. So similarly, the reverse. This is reverse boost mode. You can see here. In this case, there is no forward biasing of the diodes. So only in either side, only two legs will operate. Like only one leg. If you turn on S1 dash, it will find a path, boost operation, right? So VB2 will be boosted using the LA2 and LA1 through S2. When you turn off S2, it will give the energy to VB1. That is the lower figure. If you turn off S2, what will happen? The VB2 energy will be, after boosting, it will go to the VB1. So it is in a reverse direction. It is energy is flowing to the VB1. So that is the thing. And this is the main operation of modes for a single leg operation. The same thing applies for the other legs. But what we did is we shifted the carrier. Like if you see, this is a control diagram for the our proposed approach. So in this control diagram, you can see first for the V2V energy transfer. So this we are already defined the charging modes. Now the vehicle has come for charging. Two vehicles got connected for charging. With this, the vehicle should exchange some information for the charging process to start. So they will fetch first initially when they get connected, using the BMS or an extra controller on top of the cables. You can fetch the voltage levels of the two batteries, the energy levels or the energy rating first, the energy ratings of the two batteries, and the available energy between the two. These information you need to fetch from them, and we need to ensure that the capacitors or the DC links of the two vehicles are fully pre-charged, and you need to pre-charge, because if you go back, you see the DC link is now same as VB1, because your DA1 will conduct, the DC link will be same as your VB1, and here DC link 2 will be same as your VB2. If you don't pre-charge, what will happen is a huge inrush will flow to charge this capacitor. That may damage your capacitor. That's why we need to pre-charge the DC links and the DC-DC converters through SA1 and SA2 throughout the V2V charging. So the next one is you need to also read who is provider, who is receiver. This is just to decide in which direction you need to transfer the energy. And the next thing is you need to decide the DBC, like the mode of operation. In this, we have shown the control circuit for forward buck mode. Similarly, depending on who is receiver, who is provider, and what is the voltage levels of the battery, the mode of operation will change to reverse boost or forward buck or forward boost. It may change anyway. But The control structure is same for all the modes, only the direction of power flow will change. You will have a reference current based on, I'll show how this reference current will be calculated. Based on that, you will have a reference current and you will have current of all the IL equivalent. Like I'm saying here, you can see each phase current is called IL equivalent 1. For the phase B, it is called IL equivalent 2, and for phase C, it is IL equivalent 3. And each phase currents are measured and compared with the reference current. And the error is fed to a PI compensator. And that is compared with a carrier to generate pulses for the S1 in the forward buck mode. Similarly, only difference for the other two phases is the carrier is phase shifted by a phase delay of 120 degree, and for the other one is 240 degree. So this delay is mainly because to make the interleaved currents. So the interleaved current mainly gives a lower ripple, that I'll show in the results that how much ripple reduction will happen compared to single inductor current and the overall resultant current in the converter. So once this control is happening, it will keep checking whether the required amount of energy is transferred to the other vehicle or not. If it is no, this will be repeating. This control section will be repeating. If it is yes, it will stop the charging. This is how the overall V2V charging control will flow for the proposed V2V approach using the motor windings and the drivetrain inverter. So these are the simulation parameters which we have considered. So this is already a published paper. You can get this data in a paper also. So basically we are considering a 450 volts battery one side, and other side is a 310 volts. So basically I consider 300 volt and later increase to 310 to make some design things. Okay, and we have the leakage inductance of the motor, which will help to reduce the ripple. And these are the capacitors and inductors and the internal resistance of the battery, all those things. That anyway is paper already available in the paper. So the next is results. As I told you, there will be 3 interleaved converters because it's a three phase or a 3-legged interleaved converter formed using the drivetrains. And the resultant battery current, you can see there is almost a 0 ripple. It is a very less ripple in this C. If you can see, it's less than 5%. And you can, at the left hand side, you can see the results for different C rating. Means when one leg is operating or all the legs are operating with a lower current reference, it's only 1 C rating. If you increase the current reference, it will become 2.25 C and it will around 2.76 C. Around 3 C, you can go up to 3 C rating of the charging. This is for the results for forward buck mode, where EV1 is a provider and EV2 is a receiver. That you can even observe from the result that the current which is giving negative means it is getting charged. Getting charged is a receiver, and when the current is positive, it is discharging, the battery is discharging the energy. That is a provider. So when discharging the battery, the voltage will dip, like the battery voltage is coming down to a lower value, and when you decrease the charging rate, it is increasing. In the same way, when you are charging it, the battery voltage is increasing and it is decreasing when there is a decrease in the charging. Okay, so this is how the V2V charging happens. Mainly, you can see here EV1 to EV2 charging is happening with proposed V2V operation. This is a simulation result, and this is as we are using EV motor for the I have showed you, right? These windings LA1, LA2 are EV windings, EV motor windings. So these motor windings are carrying a current of DC currents with a ripple, like 55.1 volts, there is a ripple of 5%. So this ripple current, what is the effect of this ripple current on the EV motor? That is what we studied, and we proved that there is no rotating magnetic field. So if you see, we are designed this motor in FEM simulation. So FEM, we use the FEM software called Ansys Maxwell, which is a popular one. There are many other FEM softwares which can be used for FEM simulation to design motor, inductors, or any magnetic things or a capacitance. It gives an FEM. FEM is mainly a physical simulation where you can give material property and you can mesh the things. So meshing will make it easy for the simulation. So depending on your meshing size, the accuracy of your results will depend. So finite element method is called FEM. So that many of you may be knowing already. So Ansys Maxwell, JMag is another software which you can use for Ansys Maxwell, and this is a Flux motors like that. So there are many FEM softwares now, SpeedM or something like that. And COMSOL is another. COMSOL is maybe it's more easy, but Ansys Maxwell is user friendly. Already there are many motor examples are available. You can use them for your work. So this basically, we designed a 150 kilowatt simulation model using Ansys Maxwell FEM model. It's a 2-pole pace, like 4-pole machine with 48 slots and rotor slots and all the dimension of the machine design you can do. And it's a lap winding with full pitch. And these are the simulation results from FEM. So these are the currents with a 5% ripple be applied to the EV motor windings. And you can see at the left, right side that the torque and the speed produced due to these currents. This initially there is a very light ripple. So that ripple after a period of 50 milliseconds, which is very less. So after the 50 milliseconds, it is almost reducing to zero. The ripple is nothing but a convergence issue in the software also. It's not basically due to the inertia of the motor, this ripple won't exist. This ripple will be damped by the inertia of the motor of a 150 kilowatt. So that's not a problem. And basically the proof here is that the EV motor is not rotating due to the high frequency DC currents, which are having a ripple percentage of 5% on the DC current average of 140 amps. So this is another result showing that during charging, there is no saturation in the core. If you see the left-hand side figure, which is a normal drive mode with 1400 rated RPM, you can see the flux distribution for a 4-pole operation. So, and the maximum, you can see the maximum flux is around 1.4 Tesla. It's not more than that flux density. And if you come here, actually there is a difference in current. Like we are not charging, we are not fully utilizing the EV motor winding for around, like the capacity of the winding current is 256 amps in AC drive mode, but in DC mode 130 or 140 amps is sufficiently enough to charge the EV battery with 4C rating, so or 3C rating. So that makes like as the current has been reduced, there is no saturation in the core, and the core is fully means it is fully the flux is not very high. You can see it's around 1.18 is the max flux in this charging mode. Okay, so there is no saturation is happening, and then the motor is also not rotating. If you see the speed of this motor when it is charging, it's around 0.043 RPM. That shows that this motor is not rotating. So basically this FEM analysis is done to prove that there is no charging torque produced due to the high frequency DC currents. That is the thing. And these are the performance analysis we did, where we observed one more thing, that these DC charging currents like 20 kilowatts frequency ripple is there, and there is a 140 amps of DC current. So the DC current is not contributing to the core loss, because core loss, you all know that the core loss depends on frequency and the flux density. So flux density is anyway there because of DC currents, but there is no frequency for the 140 amps DC. The core loss component in the DC charging mode is only 5% ripple, that is having a frequency of 20 kilowatts. So that will produce a very less core loss compared to the drive mode. And basically the core losses are very less due to the 5% ripple only. And in AC it is very high because the AC is a 50 yards AC. And the other thing is, as the current is less, the ohmic losses are also less. And that is the one main option, one main advantage of the proposed approach using the EV motors for V2B charging. Like that, if you see the efficiency in the drive mode, the motor is around 92% efficiency, and there is no energy conversion in charging mode. So there is no point in calculating the efficiency, because we need to calculate the efficiency for the energy conversion. There is no mechanical energy produced, right? So in that sense, for the V2B charging mode, the motor efficiency need not be calculated. And like similarly, the drivetrain VSI, we have calculated the switching loss, conduction loss at 20 kilowatts, the switching loss, and it's around 96. The overall efficiency also we calculated, it's around 98% in the charging mode, and in drive mode 97%. So this is the performance analysis of the motor, and this is basically we compared with our proposed topology with the already existing V2B approach, and we achieved a higher efficiency compared to them. And coming to the hardware setup, you can see here we used a motor. Basically there are two motors required with a neutral connection, but we did not add another motor, so we used one motor and the other three inductors for representing the equivalent inductance of the figure, and then two semicron inverters, and the battery EV1 and EV2 batteries are 3 and 6 are EV1 batteries, and 2 and 4 are the semicron inverter modules, 3-phase off-grid modules, and the 8 is a sensor board, and 7 is a DSP controller. We used a 28335 DSP controller, and 9 is a level shifter, because these semicron drivers were requiring 15 volts as the input, but the DSP will give only 3.3 volts, so we need to level shift them to a higher voltage, and that is done by a level shifter using that. And this is the overall setup, so where we try to manage to transfer energy between the two battery banks, which is one is at 180 volts, the other one is at 210 volts or 250 volts, sorry. So this voltage transfer has happened, and we did the energy transfer between them to prove the concept that this integrated EV charging is able to transfer energy between two vehicles. So the two batteries represents the two EVs. And this is the simulation parameters. You can see 180 volts, and the other battery, EV2 battery, is 120 volts. And the battery AH rating is very less, because if you increase the AH rating, the battery size will be huge, and that is not for a lab. Like it's a laboratory prototype, so we reduced it to 3 AH. And the inductance, you can see the motor winding leakage inductance and the motor winding, these things, and the capacitors and the DC-DC converter inductance. Like this is mainly as a simulation parameters, the reduced scale of for experimental setup. So this is basically the experimental results, where we are transferring energy from forward buck mode from VB1 to VB2, where you can see the IB2 is negative 9.1 amps and IB1 is positive, means it is giving the charge, and IB2 is taking the charge. Similarly, for reverse boost mode, you can see the results. And this is the same inductor currents plotted to show the ripple in it, and it's very less ripple, like around 0.1%, you can say. This is like 4.65 amps and the ripple is around 0.5 amps. And this is shown to show that the controller is working fine with whatever command you give. Like if you command a current of 1 amps, it's increasing next 2 amps, 3 amps, like that. Again, you decreased it like that. So this is just to show the controller action. And this is again the similar battery currents with the control in the current for the experiment. Okay. So this is mainly, and coming to the existing commercial products, these are like Hyundai Kona. Already I explained you, there is a Hyundai Kona is having V2b charging. You can see that the Hyundai Kona will have a charging ports at the front. So they are getting connected through, there is 2 cables. It's not a direct connection. The dicky of the first car is open. There is a charger in it. And so that charger cable, output of that charger is coming to the first car, and the input to that is coming from the back car. So this basically V2b off port. There is one more charger in between. Similarly, there is another Andromeda company, which is also having an off-port charger to charge 2 EVs. So it can be used for generalized, like even Tesla to Nissan you can charge. So here in Hyundai also possible, but they are not given details about their V2b charger. And it is developed by some other supplier. It's not directly Hyundai developed the V2b. And this is Sona Motors. The other, this is a newly trending vehicles, which is having this black vehicle is a Sona Motor vehicle, which is a big MPV, where it is a 7-seater, but it has throughout the body solar plates. It has throughout the body of the car, it has been embedded with solar panels, and that solar panels can give around 35 kilometer range. If it is stand in a sunlight for 1 day, you will achieve free kilometer of 35 kilometer range. That is one way good. And it has also an option to charge another vehicle through the AC port. That maybe we assume there is no details about it. We assume that type 2 charger ports are connected and there is a redundant energy conversion stages here. So these are the existing V2b compared to our paper, but these are all external charger based and they are not drivetrain integrated. And this is a presentation. So I'll just take water and come back for one more presentation I have on wireless. So is that okay?
Yes, sir.
Yeah, sure.
Yes, sir. Okay.
So similar to Audible?
Yes, sir.
Yeah, sure. So similar to what we discussed, they are all cable connected, like you need to physically connect the vehicles for vehicle to vehicle energy transfer. So, but in some extreme weather conditions, the drivers cannot come out of the car or they can't get down to connect two vehicles. So in that case, we need a wireless electric vehicle to vehicle charging. So that is our next research area, which we are exploring right now. We are not yet published anything in this area. So I just thought of we can give this also for the users so that they can also explore. 2 papers are there. If they have some facility for developing the wireless charging converters and the windings or the coil pads, then they can easily do this. This is not a complex area, but at the same time it needs some infrastructure. So coming to wireless charging basically is like
Hello,
to
sir.
avoid heavy cables. Yeah.
Hello, sir.
Sure.
Sir, keep it in
Yeah,
full
tell
screen
me.
mode, sir.
Sure.
Okay.
Yeah. Sorry about that. And if you see the wireless charging, the main advantage of wireless charging is you will avoid the long heavy cables. You can, that's a very convenience for the user, EV user, mainly not for all the areas. This mainly for extreme weather conditions, or in case people are not able to come out of their car for many reasons. So in that case, the user need not to handle heavy cables, and this usually ensures personal safety, like you need not to come in contact with electricity. So even though the charging cables are safe, they are insulated, there may be a possibility that you will touch the conducting part of the cable. So in that sense, this V2V wireless V2V is a good option where we need not to touch anything. You just need to bring the cars to near for charging. So that is one, and you can automate this session, and the user need not to do anything. So your internet connection is unstable, it's saying. Yeah, is I'm audible now?
Yes, sir, but little
Okay.
voice is not breaking, sir.
Okay. Yeah. Sorry. Maybe for a moment the internet was not good. So now it's audible, I think. Yes.
Yes, sir.
Yeah.
Now it's okay, sir.
Yeah. Now it facilitates a complete automation of EV charging process. The vehicle needs to go and stand in the charging. There is parking lot where the EV charging coils are under the concrete, and the vehicle also have a receiving pad, and it will receive the car. The main design objectives for this wireless charging is basically the maximum power transfer efficiency, like how much from grid or from the other battery, how much efficiently you transferred, because efficiency is the main factor here, because the coils have a very huge basic thing here. Unit is very low. Let's say if you take a transformer, the core is coupling both the windings. There the coupling factor is 1. So coming to air core, like one of the winding is in the car and the other winding is in the parking lot or in the other car. So at that time, the gap between the two vehicles is more. At the same time, there is no core between them, a common core coupling them. At that time, the coupling factor will be very less. It will be like 0.2, 0.1. So the efficiency matters. At that time, the efficiency comes down very less. And due to the resonance, the zero phase angle is a very important aspect, where the current in the first winding, or the voltage or the current in the first winding, should have a zero phase angle with the secondary winding voltage and current. But when you park the car, there may be a possibility that the windings get misaligned. So basically, if they are aligned very nicely, I mean with a perfect alignment, there will be much more coupling factor, like the coupling factor is more. When they're displaced from each other with the angle or with a lateral displacement, at that time your coupling factor will reduce. So to increase the efficiency even in case of displacement or a disalignment or a misalignment, you need to have this zero phase angle option. So that is to improve the maximum coupling, high mutual inductance. And for this, they choose a compensation network, just because to avoid the efficiency reduction due to misalignment. They choose a right compensation network to make it a resonant converter, and they will have a better efficiency using the compensation networks. We will study what is the compensation network. And there is a CCCV control, similar to the charging, which I did not discuss in the EV charging. Basically, any EV, any battery charging will have a CCCV control. CCCV means constant current, constant voltage. Means basically you are charging the EV battery from 0 to 80% in current constant control mode, constant current mode, and from 80% to 100% in a constant voltage mode. Because if you, even after 80%, if you start pumping the current at a higher rate, the voltage of the battery will go high and the battery may get damaged. That's the reason why they control the voltage and after 80% or 90%, that depends. So that is possible even using the wireless charge. So the least converter losses using ZVS and ZCS. Because we are using resonance, we can go for zero voltage switching or zero current switching to avoid to improve the efficiency. So these are the compensation networks. Maybe the time is running a little go faster. Okay, so these are the compensation networks where you can see the a simple series block where you have a C, L, and LTX is a winding itself, the transmitter or the receiver. And so there is a series block, like with the winding you have one capacitor, that is series block. With the winding, if you have one inductor and one capacitor in parallel, that is again LCL. Like that, if you have more, you have LCCL. So these are all basically a compensator networks designed to give a resonant frequency. If you operate your converter switching frequency at this resonant frequency, your efficiency is very high. So you will compensate for the loss for the low coupling. Like actually the windings, if you don't compensate, they will lead to loss of leakage and the coupling factor is very less. So, but if you do it with resonance and the switching frequency equal to the resonant frequency, then at a high frequency, so you will have a better efficiency. That's the main concept for these couplings and the compensation networks. So basically, any wireless charging topology will be like from the battery of the EV. There will be a bidirectional current source converter or a voltage source converter with a resonance components like LC, which we previously discussed, tank circuit we call them. With that tank circuit, and it will go to the battery. So that is the main concept. Like if you are charging from the grid, the grid will have a DC-DC converter and a resonant converter, which will give the power to the transmitter coil. So after the transmitter coil, the receiver coil will be coupled with the resonance and with the compensation network. And efficiently you can transfer from the transmission to the receiver, and the receiver will again be converted to DC and it will fed to the battery. This is a usual type of battery charging using wireless charging. So there are other possibility like you can use many type of converters. So you can use buck boost converter for boosting by an active rectifier or like that. So many converter possible. So similarly, so there is another type of wireless charging. This what I discussed here is for a parking lot. So where you will have a grid supply and the transmitter coil is under the concrete and it is stationary. The transmitter coil is stationary here, and the receiver coil is also stationary. The car is also standing. But it's like when the user wants to charge during the travel, like on the go. If you want to charge on the go, on the road, under the road, you need to put these coils, the transmitter coils for every some distance, with some distance you need to provide these coils, so that when the vehicles moves on this coils, and these coils are energized under the road, they will receive the charging through the driving. So your energy is not drained. Like even after traveling 500 kilometers, you have a full charge in your vehicle, because the road is itself is charging your vehicle. So without any cable. So this is another wireless charging technique called dynamic wireless charging. So for that, they designed, in this paper, they designed a simple coil structure which is more effective and more coupling factor, by using 3 coils, 2 on the side and 1 on the top. Okay, so this is called dynamic EV charging, another type. So this like a electric railway track, you can say, for cars. So this is a huge investment, and it's not practical till now. So because you need to have a huge investment, like under the road you need to put, and to that road no one should go, a lot of things. Okay, safety issues, all those things will come into picture. This is not still practical. It's like a railway track you need to put for all the roads. So for this dynamic charging, there are topologies, like you can have a single primary converter centralized, or you can divide the converter to individual coils. Like each coil can have an inverter and resonant converters possible. Okay, so that is how. And this is another wireless charging where it is hybrid, like inductive charging, like induction. So the plates of the 2 capacitors are kept away, and with the one plate is transmitter, other plate is receiver. With the capacitive thing, it will charge. So this is a hybrid wireless topology, where you have this inductive charging and the capacitive charging both. Okay, so okay, it's breaking. I think the net is okay. Yeah, the coil shapes, like you can have multiple shapes of coils, rectangular, circular, and you can have a transmitter coil bigger and the receiver coil of a smaller size, to make the and design how you want to do. This is one area of research, and they have showed that four quad coils kept like this, and this will improve the misalignment. Even if misalignment happens due to the coil shapes, it will compensate. And the other thing is a transmitter with a cylindrical shape, and the receivers are kept in all directions to receive. This is basically for multiple coil canonical transformer. So this basically improves the coupling, even though the vehicle moves. This is basically not for a vehicle, so this is for a different application. I did not mention that application. I'll share it later. Okay, so and these are the wireless charging topologies presently available. But coming to wireless V2V, so what are the challenges in V2V is only 2 additional challenges, objectives. Like there may be a possibility that there is an angular offset. What is angular offset is, I'll show you. So like that, the receiver, this is a transmitter coil in the bottom, and there is a receiver coil. So the receiver coil may be in angular displacement, like you can see in the right side figure in the experimental setup. One is a straight coil, which is receiver, and transmitter got a tilt, angular tilt. So that may cause an angular misalignment for even the car parking or car positioning. That may be possible. That's why they are proposing a coil which is triangular in nature, triangular in shape and design. So that will cover most of the receiver coil, and it will make the more coupling between them. So with that, that is one of the paper available for this wireless V2V. The other paper is having an intermediate coil. If you see that TX coil 12 turns is one of the EV's receiver coil, and RX coil 12 turns is another EV's receiver coil. So one is transmitting, one is receiving, but in between there should be a mediator. So the mediator is the intermediate coil. So the intermediate is coil is taking the energy from the transmitter and transmitting it to the receiver. So first, basically, they propose two things. One is the intermediate coil with what is this? This is like intermediate coil with non-concentrated winding, like it's a distributed winding, right? So coming to the next coil topology, they have concentrated under the transmitter coil. There is a more intermediate coil, and under the receiver coils also there is a bigger intermediate coil, and this will improve more coupling. That's what the paper proposes, and it's very simple and evident by seeing that itself. So, and additionally, they have some compensators, as I explained, series compensator and LCC compensator. So this is basically their proposal, and they proved that this concentrated intermediate coil is more efficient due to its more higher coupling. So these are the only two papers, and you can explore this area further. And so this is what I want to stop here. The other things are still we are researching. We are not these things. Okay. I'll stop here. You can, if you have questions, you can.
Hello, sir.
Yeah, tell me.
Your presentation completed, sir?
Yes, my presentation is.
Okay, sir. Here we have some questions from participants.
Yeah.
Yes, sir. Sir, first one.
Yeah.
Can we implement wireless charging for off-grid charging of electrical vehicles?
Yeah, off-grid in the sense what they are talking about is without a grid, they want to do wireless charging. That's what we are telling. When there is no availability of grid, we are proposing it for a vehicle-to-vehicle charging. So because vehicle is easily reachable to off-grid places, like there is no grid there. So off-grid places, or if they are talking about off-grid with the renewable microgrids kind of things, isolated islanded mode microgrids, yes, possible. In that case, yeah, even your microgrid inverter will form a virtual grid, or it's like a grid forming converter. With that grid voltage, we can have wireless charging or even EV charging, anything possible.
Okay, sir. Next question, sir.
Yeah.
What are the different methods to reduce the charging time of electrical vehicles?
Yeah, charging time basically depends on the charging current. So if you can charge with a higher current, so you are basically you are reducing the charging time. Okay. So how you do it is left to you, depending on your availability of power, how much power is available to you. If you have a higher power source, like a bigger grid, like higher voltage, higher current, so depending on that, you can increase the charging current. So that's mainly the one thing. That's the basic of it. So for that, conventionally DC fast charging station is the conventional plan to reduce charging time. You can reduce charging time even with our proposed solution because it's a high power. So that is one option. Or you can, mainly you need to increase the power level of the charger.
Okay, sir. Thank you, sir. Next one, sir.
Yeah.
Can we use electrical vehicles for long distance travel? And what about the charging stations?
Yes, long distance travel is the range, even IC engines. So mainly they are limited with your tank capacity, fuel tank capacity, right? So there you have a range. With full tank, you can go up to 500, 600 kilometers. Just because presently the fuel stations or the petrol pumps are well established, you have no worries filling the petrol. But presently the charging stations are not in same proportion as the petrol stations. So once the petrol stations are established, once the charging stations are established, it's similar to the petrol stations. you can have a long run, long anywhere. You can go use it as a IC engine vehicle itself. But presently, the charging infrastructure is not so well established, but they are going depending on the EV adoption by the users. So if the more EV sales happens, everybody adopt to EVs, then your petrol stations will be less and your EV charging stations will be more. So depending on demand, the supply will be there. So if the the user should go for EV, then you will have longer distance trips without any problem. Otherwise, you need to plan your trip according to the charging stations. So if from your home, if you want to travel 500 kilometers, you can charge overnight. With that, you need to plan a route where more charging stations are available.
Okay, thank you, sir.
Yeah.
A very good afternoon to everyone present here. I hope you all had a very interesting session. On behalf of Department of Electrical and Electronics Engineering, Gates Institute of Technology, and the participants, I deem it a great honor and privilege to thank the speaker, Dr. Umesh sir, for all the valuable information he shared with us. The lecture was an interesting and knowledgeable one.
Yeah.
Thank you, sir.
Thank you very much. Okay.
Now it's time to propose.
Yeah.
Now it's time to propose vote of thanks.
Yeah.
On behalf of my team, today I take this opportunity to pull all my gratitude in the form of words. Once a great man said, feeling gratitude and not expressing it, like wrapping a present and not giving it. First of all, I would like to thank Chief Guest Professor Sujata Madam, who graced our FDP inaugural session and inspired us with her words. Thank you, Madam. I would like to thank our distinguished speakers, Dr. Muruganandam, Dr. Chilaka Rangaraj, Dr. Manoranjan Sahu, Dr. Damodar V. Shivakrishna Rao, and Dr. Umesh BS for giving excellent presentation and making this FDP interesting and meaningful. I would like to extend my heartfelt thanks to beloved correspondent Srimati V.K. Padmavathamma Madam for her encouraging words on the day of inaugural session and for her continuous support. Thank you, Madam. I would like to express my gratitude to our Managing Director, Sri G. Raghunath Reddy, sir. Thank you so much, sir, for supporting us and guiding us in a right way. I would like to thank our Director, Srimati V.K. Srivani Madam, who has initiated us to do this program and for our continuous support right from its inception. Thank you, Madam. I would like to express my profound gratitude to our Principal Dr. D. Venkatesh sir for his constant support and encouraging throughout the program. Thank you, sir. An event of this dimension cannot happen overnight. The wheels starting rolling days in advance. We have been fortunate enough to be backed by a team of very motivated and dedicated faculty. My heartfelt thanks to Dr. Syed Surya Madam, IQAC Coordinator, Co-Convener Mr. Shiva Reddy sir, and my entire team, Manohar sir, Lakshnath sir, Sunkaya sir, Abdul Rahman sir, and Reshma Madam for their continuous support in making this FDP successful. I thank Mr. Noor Ahmad sir from Mechanical Department and Mr. Narayan Swami sir from ECE Department for technical support. I thank Mr. Pawan from 4th EEE for designing flyer for this FDP. Last but not least, I thank our management and principal for giving me this opportunity. Thank you one and all. Thank you, sir. So we'll end the session.
Thank you very much. Thank you. Yeah. Sure. I'll stop here. Okay. So I'll end the session. Thank you very much. Thank you, everyone.
Okay.